Hello everyone, so today we're going to go over section 9.2, transformations of exponential functions. So we'll begin by looking at example 1. We are going to consider the graph of y equals 2 to the x, which is already sketched on the grid, and we are going to compare it to y equals 2 to the x minus 4, and also y equals to 2 to the power of x minus 4, so slightly different there. The general rules for transformation still apply, so this minus 4 here is going to move the graph down 4 spaces. And this x minus 4 power on our part B of this example is going to move the graph to the right 4 spaces. Okay, so let's look at the minus 4 part first. Since the graph is moving down 4 spaces, the asymptote will also move down 4 spaces. So instead of the asymptote of y equals 0, we'll have the asymptote of y equals to negative 4. Okay, so from there, all the points simply move down 4 spaces. So instead of, for example, 0, 1, we'll have 0, negative 3. Instead of the point 1, 2, we'll have the point 1, negative 2, and so forth. So here we go. So again, the y coordinates will just be 4 less than the original. And then, of course, we can then connect the points to draw a curve. And it will look something like this. Okay, so the asymptote, of course, will be y equals to negative 4. Notice that since the graph was moved down 4 spaces, we now do have an x-intercept. We can find it simply by letting y equal 0 or by observing the graph, and in this case, the x-intercept will be x equals 2 at this point right here. The y-intercept can also be found by just observing the graph. We have y equals to negative 3. We can also find the y-intercept by letting x equal to 0. And then the domain of the graph stays the same as before. X is an element of the real numbers. And finally, the range will match up with the asymptote. So this will be y is greater than negative 4. Okay. The second graph, we're looking at a transformation right 4 spaces. So all the points will be moved to the right 4 spaces. That means the x coordinates will increase the values by 4. So instead of, for example, here, 0, 1, we'll have 4, 1. Instead of 1, 2, we'll have 5, 2, and so forth. So it'll look something like this. And again, connect the points together to draw a smooth curve. It looks something like this. Notice that because it is a horizontal translation, the asymptote stays the same as before. It was still going to be y equals to 0. Because of that, there's still no x-intercept, so there's none in this case. The y-intercept, we're going to let x equals 0 to find out what that is. Right, so y is going to be equal to 2 to the 0 minus 4. That means we have 2 to the negative 4 power, which we know is 1 over 16. So that will be the y-intercept in this case. The domain is the same as before. Y is an element of the real numbers. And finally, the range, simply y is greater than 0. Okay, so we have demonstrated that translation works much in the same way as for other functions that we have looked at in the course. And next we're going to look at how vertical and horizontal stretches will work when it comes to the exponential function. So example 2, very similar to example 1, we are given a kind of basic exponential function, in this case y equals 3 to the x, and we're going to sketch the following. The first one will be y equals 2, and then 3 to the x power, and then after that we will have y equals to 3 to the 2x power. So what that means is, in the first case, we're going to have vertical stretch by 2 because of this 2 here. So we're going to label that as such. And then in the second case, this is going to be a horizontal stretch by 1/2. Okay. So in the first case, the y values will simply be doubled. So instead of 0, 1, we'll have 0, 2. Instead of 1, 3, we'll have 1, 6, and so forth. So the graph is going to be steeper than it was before. So it's going to look something like this. Okay. So that's the y equals to 2 times 3 to the x power function. Notice that the asymptote was not changed. So still y equals 0 will be the asymptote. Still, because of that, no x-intercepts in this case. The y-intercept is now going to be 2. Note that from the previous section we did talk about how a lot of times if the exponential function was not translated left or right, then the y-intercept is simply the a value. In this case, it is 2. So we can also find that by using some algebra, letting x equal 0, 3 to the 0 power is 1, 2 times 1 is 2. The domain, still x is an element of the real numbers, as before. And finally, the range y is greater than 0. Okay. So the next piece, we're going to have y is equal to 3 to the 2x power. It is a horizontal stretch by 1/2. However, we can also look at it in the following manner. So we have y is equal to 3 to the 2x. Now, we saw before that we can separate out the exponent and evaluate by parts. So we actually can rewrite this as 3 squared to the x, which is really just 9 to the x power. Right, so that's another way to graphing this function that could be useful in some instances. For example, if we were to do that right now, then we have 0, 1, and then 1, 9, and that's it. So unfortunately, it is a little bit hard to read what's happening because everything is on the same y-axis, but hopefully it is still okay. Okay, so it's going to be a very steep curve in this case. Again, we're just going to do our best when it comes to sketching these curves. Okay, so the asymptote, still y is just equal to 0 because we didn't do any translation in this case. No x-intercepts. The y-intercept is going to be just 1. Again, we can simply let x equal 0 to evaluate what the y-intercept is going to be. There is no change in the domain as before, and finally no change in the range either. So y is just greater than 0. Okay, so the next piece is when we start to combine various transformations together. So we are given some functions here in example 3, and then a transform function, and we're going to compare the transformation that occurred. So what we're going to do in this chapter, this unit that's different than before, is we're going to rewrite kind of what happens here. So instead of writing it as y equals to -2 and then 4 to the x minus 2 power, we're going to rewrite this as -1/2 y is equal to 4 to the x minus 2. And what that allows us to do is to isolate what happens to the y variable and what happens to the x variable. So if we look at the original function and what it becomes, we can see that instead of y, we now have -1/2 y. And instead of just x, we now have x minus 2. So if we were to look at, let's say, the 1/2 in front of the y variable, that means we have a vertical stretch by 2. And a negative sign in front of that will be a reflection over the x-axis. Likewise, when we replace x with x minus 2, the graph simply moves right 2 spaces. Okay. We can do the same thing with the second example as well. So here we're going to rewrite the transform function as negative, and then y plus 4 is equal to 2, and then x over 5. So now, if we were to isolate what happens to each variable, the y variable becomes then negative y plus 4, and the x variable becomes x over 5. Okay, so we can see here then that there's a reflection over the x-axis, followed by a shift down 4 spaces for the function. And then the x over 5 means we have a horizontal stretch by 5. So doing the question this way by isolating the transformations to the y variables and then the transformation to the x variable separately allows us to rid ourselves of some of the ambiguity when it comes to the transformation, which generally a good thing. Example 4, see here. So this is a question that we've seen before, comparing y equals to 1/3 x to y equals 3 to the x. And once again, the idea here is that y equals to 1 over 3 or 1/3 x can be rewritten as 3 to the negative 1. Sorry about that. X. So if we compare that to y equals 3 to the x, we can see that the only change is that x becomes negative x. So that will be a reflection over the y-axis. Okay. So we're going to go ahead and try some questions, example 5, parts A and B, where, again, we're given a exponential function, and then it's going to be transformed. So let's look at what happens when we go from y equals 4 to the x to y equals to 4 to the negative 2x minus 10 power, and then minus 3. Okay, we'll begin by isolating the transformation. So we have y plus 3 is equals to 4 and then negative 2. We're going to factor out the negative 2, and then x plus 5 in the parentheses. Okay, so if we were to once again look at the variables, the y variable goes from y to y plus 3. So of course that is down 3 spaces. And then the x variable undergoes a number of transformations actually. It goes from x to negative 2 x plus 5. So that is a reflection over the y-axis. Okay, that's one transformation, a horizontal stretch by 1/2. And finally, we will do the translations at the end, so that's left 5 spaces because of the plus 5. Okay, so one of the ways to handle this question then is to use a table of values now that we have isolated the transformations to the x and y variables separately. Let's see here. So I guess we're going to make a table of values for the original function, and that is y equals 4 to the x. And we're just going to use this for maybe 3 to 4 points. So let's say -1 will give us a quarter, 0 gives us 1, 1 will give us 4 for the y value, and finally 2 will give us 16. Okay, and then on the other side, we're going to have the transform functions, x and y values. Okay, so let's see how this works. So let's start with the value of x equals -1. If we are to reflect it over the y-axis, it will then become +1. And then horizontal stretch by 1/2 will make it 1/2, +1/2. And then left 5 means we subtract 5 from that. So we get -4.5. So it's going to write this down for the first one. So we started with -1. Because of the reflection, it becomes +1. Because of the horizontal stretch, it becomes 1/2. And then because of the left 5 spaces, we subtract 5 from that, and we get -4.5. So that's the thinking when it comes to these transformations. So second one, 0. See, reflection doesn't do anything. The stretch doesn't do anything. So it's simply left 5 spaces. So we're going to get -5 here. And then next point, +1, if we are to reflect that over the y-axis, becomes -1, and then the horizontal stretch by 1/2, -1/2, and then left 5 spaces gives us -5.5. And then the 2, again, -2, and then -1, and gives us -6 at the end. Now the y values are a lot easier to work with. We simply have to subtract 3 from the original y values. So instead of 1/4, 1/4 minus 3 is -2 3/4. And then 1 minus 3 is, of course, -2. And then 4 minus 3 is 1. And finally, 16 minus 3 is 13. So these 4 points on the table on the right are going to be on the new function. Now, before we graph that, though, we're going to go ahead and draw in the asymptote, which we know has moved down 3 spaces because of the translation of down 3. So this will be the new asymptote for the transform graph. Go ahead and plot the points in. So -5, -2, for example. -5.5 and -1, sorry, +1. So up here. And then -4.5, -2 3/4. So it'll be down here. Unfortunately, the point -613 doesn't fit on this graph, but that's okay. We can still use these 3 points to draw a very good sketch of the function. So it'll probably looks something like this. And there we have it. Okay, so the asymptote is going to be y equals to -3. The x-intercept, we could let y equals 0 to try to find the x-intercept. Unfortunately, right now, there's no good way to finding the x-intercept. It does require logarithms, so we're just going to estimate as to what it is. And we can see it here. The x-intercept is around, let's say, -5.4, somewhere around there. The y-intercept, however, we can find this by letting x equal to 0 in our function. So that would be to the negative 2 times 0 minus 10, and then minus 3. Okay, which of course simplifies to 4 to the negative 10 power, and then minus 3, which is going to be very close to negative 3. But not quite. So it's going to be just short of negative 3 because we know that that is an asymptote. From there, the domain is going to be x is an element of the real numbers. And finally, the range, y is greater than negative 3. Just adding to the y-intercept part, the idea here is that 4 to the negative 10 power is going to be a very small number. And then if we subtract 3 from that, it's going to be very close to negative 3, but not quite negative 3. And again, the x-intercepts, we don't have a good way of finding what that is right now. We just have to estimate using our graphs. That will we cover in more detail in the next unit. Okay, let's look at the next graph. So here, let's see. We have y equals to negative 2 and then 4 to the power of 3x minus 3 and then plus 2. So again, let's try moving, let's say the plus 2 to the left-hand side, start there. And we can also factor out the 3 from the exponent. And then from there, we can divide both sides by negative 2. So of course, what we're trying to do here is to isolate the transformation relating to the y variable to the left-hand side, and then we're going to limit the transformation relating to the x variable into the exponent. Okay, so we have y transforming to negative 1/2, and then y minus 2, which means there are 3 transformations. There is the reflect over the x-axis. It's going to write shorthand for that one. There is a vertical stretch by 2. And finally, it's going to be moved up 2 as well. Meanwhile, the x variable becomes 3 and then x minus 1. So that will be a horizontal stretch by 1/3. And then the graph moves right 1 space. So once again, just like before, we're going to start by looking at a couple of table of values. So again, we will start with the original function, which has the following points. Again, negative 1, 1/4, and then 0, 1, and 1, 4. That should be enough. And then on the other side, we're going to have the transform points, so we don't know what those are just yet. But we are going to find out. Okay. So, let's see here. Negative 1, horizontal stretch by 1/3, so negative 1/3, and then right 1, so plus 1. So negative 1/3 plus 1 is 2/3. The 1/4 now. 1/4 reflected gives us negative 1/4. Vertical stretch by 2 gives us negative 1/2. And then up 2 means we're going to get 1 1/2. Okay, second point, 0, 1. Let's start with the x variable. The horizontal stretch doesn't do anything to the 0, and then it's going to be moved right 1 space, so it's going to be 1. Very similar to the y value. Let's see here. We have 1. Reflect over the x-axis gives us negative 1. Vertical stretch gives us negative 2. And then up 2 gives us 0. So it's going to be 1, 0 on the new graph. And finally, the last point here, 1, 4. The x value of 1, the horizontal stretch of 1/3 makes it 1/3. and then right one space gives us 1 1/3. And then the y value, we start with 4, and then -4, and then -8 because of the vertical stretch by 2, and then up 2 spaces gives us -6. So those are the 3 points we have. Let's go ahead and plot those. So x is 2/3, y is 1 1/2, somewhere around here. And then the point 1, 0. So x equals 1, y equals to 0. And finally the point 1 1/3, and then -6. So somewhere down here. Now the graph is reflected over the x-axis, so it's going to be upside down, and the asymptote was moved up 2 spaces. So we'll have a graph that looks like this. This is the asymptote of y equals 2. And then the function that we have is going to look like this. Oops, sorry about that. A little bit harder to draw because of the horizontal stretch here, but just going to do our best. And then something that looks like this will be quite sufficient. So the asymptote is going to be y equals 2. We do have an x-intercept. In fact, we know for a fact that it's 1 because of the table of values that we have. The y-intercept, we have to let x equal 0 again. So that will be -2, and then 4 to the 3 times 0, sorry, minus 3, and then plus 2. And if this were evaluated, it will be approximately 1.97 using a calculator. The domain and the range, so the domain was going to be x is an element of the real numbers, just as usual, for an exponential function. And then the range is going to be y is less than 2. Okay. It's one of the first examples that we have where the exponential function is reflected upside down. So the range is going to be slightly different. Okay, so example 6, this is a bit of a challenging question. It is about finding out what the transformations are if we're given the original graph and then the transform graph. So we can see here that the original function was y equals 5 to the x, for example 1. And we can also see that we have 3 points here. The first point is 0, 1. The second point we're given is 1, 5. And the third point is 2 and then 25. And the idea here is that those 3 points correspond to the 3 given points on the transform graph. So that is to say, the point 0, 1 maps to the point -3, 3. The point 1, 5 maps to the point -2, 7. And finally, the point 2, 25 maps to the point -1, 27. So we can see that all of the x values decrease by 3, and all of the y values increases by 2 as we go from the original function of y equals 5 to the x to the transform function. So all we need to do is write down the transformation that lead to those changes. So that is to say, instead of y equals 5 to the x, we have y equals 5 to the x plus 3 because all the x values were decreased by 3, and then plus 2 because all the y values were increased by 2. Okay, so that's a relatively simple case of this kind of question. Example B is a bit more challenging, but kind of the same idea applies. So once again, we have the points 0, 1, this time 1, 2, and then 2, 4. And those 3 points will match up with the points in the transform function here, here, and here. So what we need to look at is the kind of transformation that happen. That takes us from the original to the transformed. We're going to list them out. So the first transformation that is obvious is that there is a reflection over the x-axis because the graph is upside down. Okay, the second transformation is that the graph was translated down 4 spaces. Because the changing the asymptote from y equals 0 to y equals to negative 4. We can also see that the x values of 0, 1, and 2 on the original function becomes 1, 2, and 3 on the new functions. So we can see that this is also right one space. And finally, the last transformation, which is the very challenging one to figure out. If we look at these two values here, specifically the y values, there is a difference of 1. Whereas the original function, these 2 points have the y values have a difference of 2. Similarly, in the first 2 points, there is a difference of 1, whereas in the transform function, these 2 values have a difference of 1/2. So what that would suggest is that the y values, instead of changing by 1 and 2, they change by 1/2 and then 1. That means we must have had a vertical stretch by 1/2. Okay, so those are the only 4 transformations that takes us from the original function to the transform one. And what we need to do now is to write a function that summarizes all of them. So we're going to have y equals to negative 1/2 and then 2 to the power of x minus 1 and then minus 4. Okay, so going from left to right, the negative sign matches the reflection over the x-axis. The 1/2 is for the vertical stretch by 1/2. The x minus 1 instead of x is the right one space, and finally minus 4 gives us down 4. So a bit more challenging example there. However, that is the extent of the transformations that we need to know for the exponential function. Again, that is the reflections, stretches, and the translations. So that's it for today. Once again, thank you for listening.